Hi, and welcome back. Now that we've defined what we mean by a system and a system of systems, let's finally get around to talking about what is systems engineering. I like to think about systems engineering in three different distinct ways. Number one, systems engineering is a way of thinking. We're going to talk about concepts like life cycle, design synthesis, a technical approach. Those sorts of things require the systems engineer to think in a certain way that's different from the other engineering disciplines that are around them. Next, we can think about systems engineering as a process, right? There is a process. There is a guide that leads us from point A to point B as we navigate through the complexity of coming up with a new system. We're going to do preliminary design, then we're going to hold a review, then we're going to do detailed design, we're going to hold another review, and we're going to build, we're going to test, we're going to verify things, we're going to field things, we're going to sustain things, right? There's a process that guides that whole thing. And then the third way I like to look at it is systems engineering is a person. There is a person who carries the title systems engineer, and they do that. They make a great living out of doing that. It's a very fulfilling and exciting way to spend your weekdays developing something that has never existed before, and then making sure that that thing is actually what the customer wanted when they started out in this long development process. All right, so let's dig into this a little bit more. Let's go back to my three favorite references for definitions, just remaining consistent with the last couple of videos. Let's start out with Nkosi. How do they define systems engineering? Well, to them, systems engineering is an interdisciplinary approach and means to enable the realization of successful systems. It focuses on defining customer needs and required functionality early in the development cycle, documenting requirements, and in proceeding with design synthesis and system validation while considering the complete problem consisting of operations, cost and schedule, performance, training and support, test, manufacturing and disposal. Systems engineering considers both the business and the technical needs of all customers with the goal of providing a quality product that meets the user needs. All right, quite a mouthful. So what are we talking about here? Well, highlight some key words for us here. We hear interdisciplinary, right? It takes a village, all kinds of different engineers, manufacturing, quality, management. It's a real team effort to get these things done. Next, what we're focused on, customer needs, right? We don't want to lose sight of that along the way, which is easy to do. Human nature sort of drives us to do the very best that we can, but that's not really what we're asked to do. We're not asked to design the very best thing that can be designed. We're asked to design the thing that the customer asked for, right? And then we want to stop there. Otherwise, we go beyond that. We're spending more money and taking more time than they had intended. Next, we see that systems engineering was really focused on early in the development cycle, right? So why is that? I'll spend some slides later on really justifying this, but from a top level, the reason is that this is where the concrete is cast, right? So beyond this, once we get the design established, everybody else for the rest of the lifetime of that system is going to live with the consequences of decisions that we made in the early stages of development. And then we see that systems engineering includes consideration of things like cost and schedule, right? That's where the management side of this is going to take place. And we'll spend some time later in the semester talking about that. At the Department of Defense, they define systems engineering as a methodical and disciplined approach for the specification, design, development, realization, technical management, operations, and retirement of a system. Right? There's the systems engineering life cycle spelled out for you. Systems engineering applies critical thinking to the acquisition of a capability. It is a holistic, integrative discipline whereby the contributions from across engineering disciplines, structural engineers, electrical, mechanical, software, safety, human factors, reliability, are evaluated and balanced to produce a coherent capability called the system. Right? And so a lot of overlap between what the DoD says here and what Nkosi said on the last slide. So I do want to just bring out one thing is that, again, this is really based around a defined capability. And it's that capability that we want to design to in the system engineering process. And finally, our friends at NASA define systems engineering as a methodical, multidisciplinary approach for the design, realization, technical management, operations, and retirement of a system. I think one thing of note here is that it's nice and short, and I think there's something to be said about that. That's important, right? By keeping it pithy, we avoid confusion. Additional words leave additional opportunity for differences in interpretation. And that's something that we're going to want to watch for when we define systems engineering processes. Let's have a look at some diagrams of the systems engineering process. And we'll start with one by NASA from their systems engineering manual. So let's start by looking at the left side of this diagram. And we'll note that right from the start, we see requirements flow down from level above, right? So when we start out with the conceptual design of a system, that starts from the very top level of the system and works its way down to lower levels of definition. And then when we start the product realization, putting things together, we're going to start that from the bottom of the system product structure and work our way back up. Right? That's going to be the natural sequence of things. So let's look at their system design processes over here. These 4 activities that are going to take place over in that part of the diagram. So those 4 system design processes, those are used to define and baseline stakeholder expectations. When we use the word baseline, what we mean by that is that we want to create a record. And then at some point in the process, we want to be able to say, okay, we've done enough. This is done to the degree necessary to move forward with the design process. And so we're going to kind of snap a chalk line there, and we're going to call that a baseline. We're going to use that term in a couple of different ways as we study systems engineering. But establishing the baseline means that we're creating that record, and then we kind of want to make the record hard to change. We're not completely closed-minded to changes, but we want to make it a bit of a difficult process. We want to ensure that there's a conversation there, kind of like changing the Constitution, right? So continuing back on with my 4 system design processes there, the other things that we want to do there is generate and baseline technical requirements. All right, that's step number 2. We want to decompose the requirements into logical and behavioral models. Decomposing requirements means that we spawn additional requirements from top-level requirements that contain more detail and more fidelity that are going to be helpful to drive the design process. And finally, we want to convert those technical requirements into a design solution that will satisfy the baseline stakeholder expectations. All right, let's swing around now to over this side where we see product realization processes. And you'll note that those are sequentially numbered starting from the bottom and going up because of what I explained earlier. So the product realization processes are applied to each operational mission product in the system structure, starting from the lowest level product and working up to higher level integrated products. These processes are used to create the design solution for each product, either through buying, coding, building, or reusing, and then to verify, validate, and transition up to the next hierarchical level those products that satisfy their design solutions and meet stakeholder expectations as a function of the applicable lifecycle process. And finally, let's look at this middle column here that's titled Technical Management Processes. As I've mentioned, there is some overlap between systems engineering and program management, and here it is. The technical management processes are used to establish and evolve technical plans for the project, to manage communication across interfaces, to assess progress against the plan and the requirements for the system products or services, and to control technical execution of the project through the completion and to aid in the decision-making process. Okay, let's look at the DoD systems engineering process model, otherwise known as the V-diagram. Overall, in the V-diagram, the way we put this to use to visualize the systems engineering process is we want to imagine that we're starting up here in the top left corner of the V, and we start with an operational need. All right, so we've identified a need for a capability that I do not have. And as I follow down the V, following this arrow that says decomposition, I am performing these processes. And you'll see some overlap between what the DoD says and what NASA had to say. So we're going to define stakeholder requirements. We're going to do requirements analysis. And we're going to do architecture design with the intent that once we've gone through those processes, we end up down here at the bottom of the V with a design, and we are ready to start heading up the right side of the V, realizing a product that is going to meet those requirements. And so now as we come back up, we are implementing, integrating, verifying that things meet requirements, validating that I actually ended up with the thing that I needed, and then transitioning that into production so that it can be fielded to the end user. And similar to the NASA approach, there are these technical management processes that are kind of listed off on their own, separate from the V, because they are going on, in concert, in parallel with all these other activities happening. The other thing that I like about the V diagram is that we have these arrows that point back and forth from the downside of the V to the upside of the V and vice versa. And what we're trying to express there is that we are learning as we move down the V, and we're also learning as we move up the V, as we're building, testing. And there needs to be an exchange of information, because this doesn't just happen once, right? That by the time we're heading back up the right side of the V, somebody else is heading back down on the other side, either with a capability improvement or the next best thing that's going to be developed based on that legacy product. Even space programs, right, that go up into space and we can't touch them anymore because they're up there and away from where we can get to them. This still applies because there's going to be a follow-on to that system that's going to learn things from the way that system was operated. And part of systems engineering is being able to capitalize off of those lessons learned and make sure that the next people can benefit from them. Okay, I've mentioned this word phases of the systems engineering process a few times, so what do we mean by that? So here's two good definitions of phases. We have the NASA set of definitions, and they kind of walk through a phase A, B, C, D, E, and F. Definitely catering toward manned space flight. So we're going to start with concept studies, do some technology development, further that technology development in a preliminary way, in a final way, get to a single phase of system development or assembly, integration, test, and launch, and then we go into operations and sustainment, followed by closeout. So those are the phases of the system engineering process in the eyes of NASA. Next, let's have a look at what our friends at the DoD have to say about their phases, right? So in their case, we see that they start with a pre-acquisition phase. A lot of the DoD process is aimed at making money spending decisions. So a lot of their systems engineering process is oriented towards supporting funding decisions for big long-term kind of programs, right? So we see that once they've decided that they want to start a new system, they're going to go into something called a material solution analysis phase. And the purpose of that is to look at a capability gap, a stated need, and determine whether the solution to that need is really building a new thing, or can we just do a better job with the stuff we've already got, right? Can I build more of them? Can I build better training systems? Can I enhance them to make them more capable? Or do I actually need to go and build an F-35 because my F-18s just aren't good enough anymore, right? And that's the purpose of that material solution analysis phase. Next, the DoD takes us into this technology maturation and risk reduction phase. So this is preliminary design. This is prototyping, those sorts of studies. And they will culminate with a PDR and then transition into EMD, engineering and manufacturing development. And that should take us through CDR, right, which is going to be our critical design review or the end of design. But we're not done. We're going to go from there into building a production representative article. We're going to perform qualification testing on that. And then we're going to confirm that we really like the thing that we have by doing these things called a physical configuration audit and a functional configuration audit. And those are going to, again, create new baselines for me to say that I really like the thing that I ended up with, and I'm ready to take it into low rate initial production at the milestone C decision. And my next phase of my systems engineering process then goes into production and deployment. That gets me from my initial operational capability to my full operational capability, and then I transition to my final phase of operations and support, which consists of sustainment and finally disposal. So those are the phases of the systems engineering process for two different government customers. Okay, so throughout that, there is without a doubt a role for systems engineering across those entire phases. And those phases could last for many, many years for a single program, right? So throughout there, the role of the systems engineer is going to be to, number one, tailor and manage to the systems engineering process, right? So that is going to be each subsequent phase of the process, each subsequent system, subsystem, component is going to be managed by a different group, a different organization, different company. And the systems engineers at each level are going to have to make sure that they are integrated into the overall systems engineering process. Key role of the systems engineer. Next is they're going to have to define requirements and then lead that whole process of requirements analysis and decomposition. We'll spend a few classes dedicated just on that. Systems engineers play a key role in managing risk, as we'll get to when we study the risk and opportunity management plans or management process. The systems engineers are going to play a key role in developing design options. And along the way, we want to make sure that we don't fall in love with the plan. In the Marine Corps, we had a saying that said that a plan is but a point to deviate from, and that's definitely true in the aerospace industry. We need to keep an open mind to better ways of doing things to meet the customer needs. The system engineer is going to lead in the planning and the execution of the program's technical approach. They're going to play a central role in the preparation for design reviews. They'll really step into the spotlight for those and try to stitch together a lot of disparate inputs to the story to tell one holistic story about how the design effort's going and what we've accomplished. Systems engineers will prepare decision analysis tools by leading trade studies. And then they'll play another key role in defining system interfaces. None of this happens in a vacuum. We all have to play in one sandbox and play well together. And so that interface definition will become key. So the system engineer is going to play a key role all the way across that entire life cycle of systems engineering. It won't be the same person. There'll be a lot of handoffs along the way, but there's a lot of work there to do.